Hi, everyone, and welcome back. This is Brahim Siddiqui. Today, I'm going to reinforce on the risk appetite sensitivity factor and the risk premium, exactly what we have done in the previous week. But we will, this time, we will derive some interesting insight. Based on the previous slide or previous video, we derive the mathematical formulation of the risk tolerance, which is risk appetite sensitivity factor C time the cost variation or risk premium. And, and we demonstrate that when the risk premium decrease, risk appetite sensitivity factor increase. And this is exactly when the reverse, when the risk appetite sensitivity factor the decrease, then the risk premium increase. And we have shown this in this formula. So you can see that when risk premium is low, then the risk appetite sensitivity factor will be high. And we said also that the risk appetite sensitivity factor represents the resilience team, the team resilience, how much stiff they are, how much is it strong team or weak team. And also we derive the mathematical formulation for the PSI or the risk appetite sensitivity factor. And then we said that it depends only on the systematic risk beta. And also I will repeat that beta systematic risk will have its own video, but for the moment, just take this formulation, which is a covariance over variance, and which can be written also by the correlation between the portfolio. Note that when we say correlation, standard deviation, and covariance variance, so which means that you have some historical data that you are trying to compute this systematic risk. Also, when you look at the standard deviation, somehow represent a risk. And when you look at the correlation, it gives you the direction. It could be negative or positive. This correlation can be negative or it could be positive, which indicates whether the that activity or that particular month, it all depends on the context that you are analyzing this systematic risk. It could be risk averse if the correlation here is negative, which means beta will be negative, or positive if it is risk seeking or risk loving. So we will elaborate more once I start doing some elaborating more on the systematic risk. Also, we define that the risk tolerance is also equal to risk 2 beta H, and consequently the the risk tolerance psi times delta x equal to beta H. From this relation, we can derive the expression of delta x, which depends on the resilience and the systematic risk of the team. So beta over risk appetite sensitivity factor as an overall represents the the strong team and the weak team, because the psi depend also on the beta. If you know beta, you know psi, then this expression beta over psi, it's a function of systematic risk. Okay, and also from the graph, if you remember, so there is a special case where the systematic risk, when the systematic risk equal 0.3017, we found that the risk appetite sensitivity factor equal to 1. And if we substitute this into the expression, so which means that if this equal 1, then risk premium or delta X equal to the risk tolerance. And we know the expression of risk tolerance, which is 2 beta H. Then we just substitute this, and we have this expression. So which means it is, this is the, in case the risk appetite sensitivity factor equal 1, the cost variation or risk premium will be in absolute value, of course. It could be negative, 60.34% of the payoff H. And also, if you remember, in the first videos, we talked about the high cost and the low cost, and we said that the XCE, which is the certainty equivalent cost, or future cost, or actual cost, depends on in its context, equal the low cost. It's between the low cost and the high cost. Basically, if you look at the graph here, this is the low cost and this is the high cost. You have X0 and your XCE vary between the low range and the high range. Now, if we, and then we know that delta X is XCE minus X0. So which means XCE is delta X plus X0 here. Then we do some simplification here, and then we substitute delta X to beta H. We just derive it from above. And then we simplify. So X0 will be simplified. Then you get this expression, and we can further simplify with the H. Then we get this between so we will have this between -1 2 beta H, sorry, 2 beta over psi plus 1, and then you bring these two from here. So you get this ratio. Okay, so make sure that your systematic risk over your risk appetite sensitivity factor should be less than 0.5. Okay, so this means that this expression is less than H, which means that delta X must be less or equal than H. Remember that delta X is this one. Okay, this is what we define by delta X. And when you do projection here, you get XCE. And this will be your XCE. And for this curve, and it has this risk tolerance. So and you can see that delta X should be or must be less than H, which is this value. Okay. This is how we define when we define the utility function and or the satisfaction function. So now we have, if we bring this here, we will have delta x over h, and this means that if you take the risk premium over the payoff, the ratio must be less or equal to 1. If you get something 2, then you are out of the range, you are out of control, your costs are, I mean, you are not managing the project properly, okay? And also, if we substitute delta x with x0 time the distortion, we can get the limit for the distortion, which is h over x0. That's it for today, and hope that you learn something from these videos. And then next time we will start very interesting topic, probably the systematic risk. So, and also keep in mind that all what I'm doing right now is just to, it's the building block. I'm just building the tools that we will be using for the control theory. Once we define the second order differential equation, the governing equation of the project control. Thank you very much, and talk to you soon. Bye.